and she'll be talking about intrinsic properties of the gamma vector and matroids.
Oh, hi. Thanks a lot for having me here, and it's been a lot of fun here in Daejeon. So, yeah, so I guess I'm talking about intrinsic properties of the gamma vector and matroids. All right, so wait, is this going? Wait, what? Okay, whatever. Anyway, yeah, so it turns out that our main character connects a certain collection of, whatever. Okay, fine. Okay, I'll start. Okay, yes, we know what the title is. Okay, so it turns out that our main character connects a lot of like combinatorial invariants that look really different for each other. So this includes things like permutation statistics. So like, I guess Shinche already like covered a lot of stuff like ascents, descents, just numbers go up and down when you switch order or not. And Euler characteristics of non-positively curved manifolds, this is where the flag condition comes from. So like being the clique complex of a graph and certain cubical complexes, but anyway. And also, how do you triangulate boundaries of polytopes? And so the gamma vector is usually like, in the setting of something like a reciprocal polynomial. So you flip the polynomial coefficients around, it's still the same. And we care about this expansion. Okay. And just using the same thing, you can do this another way of rewriting it. It turns out we'll use this somewhere. And so here's an example. This is a permutation. It goes down and up twice. And so I think one of the first places where some precursor of the gamma vector appeared is like studying like Eulerian polynomials and ascending, descending permutations, like thinking of continuing fractions and stuff, and work of Wada and Schützenberger. And so for this particular case of Eulerian polynomials, we can consider like the Eulerian polynomials themselves as like generating functions for a number of descents. And the gamma vector, you have the additional condition of avoiding like double descents or final descents. But the thing is that there are a lot of ways to express these, and if you switch like descents with ascents, descents with ascents, you'll get the same thing. So here, we are skipping descents, but are we happy if we switch like descents with ascents here? Okay, I guess it's pretty obvious that we're not happy. All right. Okay, so why do we care about the gamma vector? Well, okay, so the positivity, according to like the guy who actually first called this the gamma vector, like Soohyun Park, says that it implies a sort of lower bound theorem. So what we mean by a lower bound theorem is if we have some sequence of like numbers and we look at like, we know that they're increasing, we can look at consecutive ratios, let's say hi over hi minus 1. And if we have a lower bound on this, it says, oh, it increases at much blah blah quickly. This is actually a thing in geometric combinatorics. And the thing is that the positivity, as Shinche mentioned, is somewhere in between like real rootness and unimodality. And unimodality is just like numbers go up and then down. Maybe they just stay the same somewhere. I don't know. Okay, so the thing is, before I give you the spoiler, there's like a lot of interesting work in this area, especially related to the topics I mentioned before, like non-crossing partitions and so on. But all the proof techniques are like very different depending on like what sort of field you're thinking about, I guess. And so like as a whole, like especially if you just think about like the generality of flag complexes, it's like rather poorly understood, except for like the top vector possibly. Even that needs some additional conditions. And in that setting, you can think about it by work of Long and Reiner as a signature of certain torque varieties when it makes sense to say that. And okay, usually it involves derivatives, but I'll get into that later. And so the general question we'd like to explore today, which is like fairly informal and like based on stuff I just started thinking about recently, is what is a gamma vector and how do you construct a general framework for understanding it? All right, so another perspective, making use of that like weird formula below and thinking of compositional inverses is like, okay, so it turns out that there's an explicit expression for the gamma vector using the derivative of this thingy. So if you're familiar with like Stanley Reason rings of simplicial complexes, so it just means that if you take a simplicial complex and you look at the polynomials which are supported on like faces of this thing, you can express it like this. So, okay, what does this do? Just as a start, like it kind of extends the definition to like whatever polynomial you started with. And you can actually use this to say some like quantitative stuff about like signs and structural properties of the gamma vector. Okay, so just to like take this format for a test drive, it turns out that at least somewhat heuristically it says something about local global properties of simplicial complexes. So let's say delta is some simplicial complex and F is some subset of the vertex set. What we mean by local has something to do with like faces that contain a particular subset, like called a star, or I can just remove the link. So it's like in the neighborhood, but not that thing itself. So let's take this particular simplicial complex. What would be the like link of the vertex here? Any volunteers? No one? Yes, good job. I see like some hand signs doing this. Yeah, so yeah, that's the link. The star is this entire thing, and then we have the sad little island there that doesn't belong to either of these. And so if we take a look at the h vectors, the h polynomial or something, it's kind of like a local global difference. So this is a local part, and this is a global thing. Okay, so now like here are some random, somewhat less random examples. Like we extended this to arbitrary things. How does this behave on like things we care about? So I guess if you like matroids, you probably like certain things like characteristic polynomials. So if you think about like let's say a lot of like boundary complexes of simplicial polytopes, there are like infinitely many of these where things are also negative. And so there are also some natural examples to consider that we care about that where the gamma vector could be negative. I think that's kind of the point here. But like, how did we arrive here? So it kind of goes back to the initial point about the lower bound stuff. Because if you look at the paper where this vector was defined, he mentions that like positivity implies lower bounds, and in the statement about the conjecture of the non-negativity, we should think about it as a lower bound conjecture. So how about the other direction? Like, can we try testing this? So, okay, first we just like try to figure out what's going on by testing random things. So if it's alternating signs, then we alternating numbers. But let's say it's actually non-negative, like most of the examples we care about. So it turns out that if it's decreasing, then okay, we get some alternating signs. And if it's increasing, which is kind of the case for more examples involving, say, like polytopes, then if it increases a little too quickly, a lot of things are negative. So I think what is going on in like what he really meant is something a little more using the intrinsic structure of the simplicial complex. So this indicates that there's more going on. So we need a little more information. That being said, yeah, is there a question? Okay, I guess I'll just go ahead then. Okay, so other stuff that's like, okay, why else would we want to generalize? It kind of relates to some natural geometry and combinatorial questions. So before I go over any of this text, I don't know if you're familiar with like Bézou's theorem, but like there's this thing about like if you have like two plane curves of degree D and E, you usually generically expect them to intersect at DE points. And a higher dimensional version of this with like more hypersurfaces and some projective space is to, just leave them there and then just intersect with some collection of hyperplanes to force it to have a finite number of intersections. And in that case, you also have the expected number of intersections is like whatever the product of the degree is. But let's say instead of taking some collection of hypersurfaces, like polynomials, let's say, that are generic among like all the polynomials of a given degree and number of variables, let's say we restrict a particular vector subspace of that collection of polynomials. Then what's the difference between the behavior of the intersections taken from hypersurface generic here versus everything? And this can be related to something called like a Segre class of like a vector bundle. And if you just take a look at the formula, like you have this like 1 plus t to some power, and if you rescale, you can think about like t as like a rescale version of a hyperplane class. And okay, so why do we care about this from a combinatorial perspective? So if you kind of paste this with like recent work of Alufi on constructing Lorentzian polynomials out of these things, you can construct like log concave and Lorentzian polynomials in a pretty simple way using the numerator and denominator out of these things. And if you're not familiar with Lorentzian polynomials, I'll tell you a somewhat pleasant lie. Namely, let's say you take a polynomial and like you take the monomials that actually like appear in a polynomial, like they have non-zero coefficients, and they have corresponding 0, 1 vectors. And then you can take like the polytope after you take the convex hull. And one question you could ask is like whether this comes from the Matroid-based polytope of some thingy. Pardon? Oh, it's like something from the derivative of h. You can literally like compute it from this. And
It's not J.
no, it's like just using the quotient rule. But if you translate by 1, you get something that's a bit nicer, like kind of more like directly like a reciprocal, and then taking a derivative. All right, so okay, so we have these like new applications, but how about like the usual like context that people consider? So to do that, we kind of go back to like, okay, what's another way of expressing this stuff? Because sort of lying under the hood is actually thinking of what's in the compositional inverses. And then we get a bunch of Callan numbers, and I think everyone likes Callan numbers, but like, what is this? So I can say a bit more about how this kind of like, I don't know, heuristically connects to like examples related to non-crossing partitions, but the main thing we'll actually use today is just that there's some kind of compositional inverse we can write down concretely, and those come from general function of Callan numbers, like t over 1 plus t squared. So just as a recap of like the setup, so reciprocal polynomials, we mean like the usual setting like Shinche mentioned, just like like if you flip the coefficients around, it's still the same. So this includes a lot of the things we care about, like H vectors of simplicial spheres. So you can just think of like H vectors as like equivalent information to like something called the F vectors, number of faces of each dimension, and the H vector is just like a form that's nicer for algebraic considerations. Eulerian polynomials, just like the generating function for descents or ascents or whatever you feel like it. Chowings of matroids, which Shinche discussed in quite a bit of detail, and then M0 and bar, who we just met in Dongwon's talk. So the funny thing is that despite like the varying proof techniques, as I mentioned earlier, something that's persistent among examples where combinatorial interpretations do exist is that there's some kind of descent statistic going on. And so, okay, how are we going to try to approach this? So the idea is to kind of combine our sort of strange approach with the earlier like usual basis, right? So this usual expansion here. And so I guess since we have this palindromic polynomial, you can be like, I want to think about a simpler problem. This is way too hard. And so a basis for such polynomials is just like, you can take the obvious one, like x to the k plus x plus d minus k. And then just leave this over here and say, oh, we have a basis of gamma vectors. But I claim that something is going wrong here. Can someone tell me why? It's something I omitted somewhat intentionally, but not really when I say this. But look at the right side. No. No, look, I believe in you. You can do this. Okay, so h has degree d. But what happens when we put x to the k plus x to the d minus k on the left? What's this? Pardon? Oh, sorry. Okay, fine. I made a typo, okay? Yes, okay. I'm a very careful person, right? Okay, just ignore the t issue. Okay, then it's simply that the degree is d and we should put a different exponent here if we were to actually say we have a bunch of gamma vectors, which is kind of false. So as usual, like when something goes like doesn't look quite right in real life, you just go on with it anyway. So, okay, well, how does that actually help us? Well, the thing is that, okay, this just happens because we made it happen, but the interesting part is that they satisfy a special recursion. And that actually gives us some, in my opinion, meaningful information. Hopefully you think so as well. So it turns out that if you look at this like explicitly, essentially the gamma polynomial is a sort of inverse Chebyshev expansion. What I mean by this is that if you take the, like, I don't know, reciprocal polynomial, let's say, just like flipping the coefficients, it's literally just like this expansion where you have like you list the coefficients backwards and then you put the corresponding Chebyshev polynomial. And there's like extensive theory of Chebyshev polynomials I'm not really going to get into. Like involving continued fractions, other combinatorial things, and even like computational algebraic geometry. But the point is that we can actually use this to give, like, say something related to geometric combinatorics of the initial polynomial that we started with. Okay, so why? Okay, so I'll give you a vague-looking series of statements and hopefully make them more believable by the end. The background's a little involved, so I won't get into every single detail, but hopefully you'll end up a little happier than you are right now. So. Okay, so the thing is that it turns out that these are closely, the gamma vector construction is closely connected to F vectors of certain kinds of simplicial complexes that arise from like special, like subdivisions of a certain kind. And they're basically certain repeated edge subdivisions, and one thing that does is like take a type A Coxeter complex to a type B one, for example. And I mean, apart from that, it kind of helps us decompose things into building blocks, and if we take like an appropriate lift of these Chebyshev polynomials, it actually turns out that we can think about these as linear combinations of boundaries across polytopes. And like, if you care about like flag complexes and like these like clique complexes of graphs and balanced simplicial complexes, which just mean like decolorable d-1 dimensional things, like which come up a lot in these like flag sphere type considerations. These are pretty basic building blocks. So they just kind of like pop out of the gamma vector even if you don't really assume very much, which is kind of funny. And apart from that, this lift that we discussed in part 2, there's like a topological analog of descent statistics, which involves the material Shinche like referred to and gave slight spoilers, but just enough to make these a little less scary. So the cross polytopes, what I mean by them, are just like the convex hull of the like plus minus EI, where EI are the usual like basis vectors. And first you start with a square, and then you have an octahedron, which everyone seems to like for different reasons. And then this goes beyond my drawing capabilities, so I'll not draw them. Okay, so the main like connection between our sort of like, I don't know, like very explicit expansion and geometric combinatorics is from work of Hetye. And I'm just using this spelling convention here just to distinguish between like different parts and just, I don't know, follow the source that I'm using. So the Chebyshev subdivisions, they're repeated as subdivision. It's not, I mean, technically it isn't ordering, but for our purposes it doesn't matter, because no matter the ordering you choose, you get the same like F vectors for the output simplicial complex. And another fact that I didn't write here is that it preserves the topology of the simplicial complex, so it's homeomorphic. So the funny thing is that if you take a look at this linear transformation we mentioned earlier, so like what we did previously is like almost doing this, but like listing the coefficients backwards, is replacing the monomial powers by these Chebyshev polynomials. And one nice thing is that if you started with something like the F polynomial of the simplicial complex, it sends it to another weird version of this F polynomial. Okay, so what is this like weird thing I'm referring to? So instead of the usual generating function for the number of faces, you replace like x by x minus 1 over 2. This has to do with certain like quote unquote like stability conditions, like sizes of roots and so on, but I'm not going to get into too much detail. But in any case, this is an indication that this transformation that we had earlier is kind of fundamentally connected to like combinatorial information with the simplicial complex. So just to give an idea of like what's going on, let's take our favorite lattice, whether you're thinking about matroids or not. I didn't write the top and bottom down, but anyway. Basically, you just have a set like 1 to n or 1 to 3, and then you just list the subsets as so. And the order, okay, so where do we get these subdivisions? Okay, so to give an idea, let's say you have a post set versus like the post set of intervals. So you just take the intervals and order them in a certain way, as you might be able to see from the diagram, like comparing the endpoints. And then the way we like get from post sets to simplicial complexes as usual is to take their order complexes. So basically what you do is like take the elements of your post set and then kind of look at like chains which are just like paths that lie inside, like corresponding to totally ordered subsets. And as you can see here, like taking the post set intervals gives you a subdivision. And so why do I care about this? Okay, so this type A to type B thing, like you can look at it comes from like the order complex of this Boolean lattice, which you can also think of as like the lattice of flats of this uniform matroid. And here you have the Bergman complexes, so like flags of flats here. And then if we take this like to be the set of intervals here, this takes us to the just the phase post set of the n cube. So it's like there's some type B shenanigans going on. And then, okay, so where do these like descent statistics come from? Okay, let's like start. Okay, this has something to do with post sets, as you've probably realized already. But let's start with things that actually come from like descents and permutations. So the source of this descent statistic that we'll discuss is like from maximal chains on post sets. So that is, the chains I said are just like paths inside the histogram or totally ordered subsets, and the maximal chains just go all the way from the bottom to the top. And as you can see here on the Boolean lattice, what do we mean by permutations? Well, first we need to find a way to label the edges here in some way. And here we're just gonna put like whatever we like added to get from here to here, or removed to get from here to here equivalently. And if you start from the bottom, you get the permutation 2, 3, 1. And so in this case, what you mean by a descent is exactly what you think it is. It's just things go up and then down, so no order reversal, order gets reversed. And the funny thing is, like, as Shinji mentioned, as like recently, like until very recently, there was like no combinatorial interpretation of the gamma vector associated to Chow rings of matroids. But in very, very recent work of like Christian Stupp, maybe it came out on the archive, maybe like July 8th or something. There is a sort of descent statistic interpretation of the gamma H vector, which leads to the gamma positivity, involving like certain labelings of Maxwell change of on a post set, namely the lattice of flats on a matroid. Okay, so like what do we mean by like a topological thing, right? So we'll get a little into that and then hopefully say something that sounds slightly reasonable. So, okay, this is a lot of text. I'll eventually make this somewhat understandable. So as Shinji mentioned, a key object here is something called the rank restricted poset. So you just take the poset you already have, only take the intervals lying in a certain subset, and then you just inherit the ordering you already had previously. Now here, what we mean by topological descents is that, okay, so it turns out that, sorry, wait, what is this doing? Okay. It turns out that if you care about the topology of these rank-restricted things, then descents are pretty natural to consider. So if we have a reasonable labeling, which I'll describe this in vague detail later, the topology of these rank restrictions depend on basically the maximal chains, where the ordering being reversed from what you would expect is equal to that set. So it's going above, but the label gets smaller. And this forms a basis. And CO shellable, I'm not going to describe this in detail, but often this sort of this family of labeling results, blah, 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 it comes up on if you want to try to understand the order complex of the poset. And there's this condition called shellability on simplicial complexes, where it's a certain nice, it basically says that there's a certain nice way of building your simplicial complex facet by facet, where at stage k, your facet intersects whatever you had at stage k minus 1 in a nice way. Okay, so why am I saying topological, right? If I had this, then it would actually be a descent statistic. So I will eventually mention that later, but so there's a topological notion of descent, which I'm not going to define, but the point is that it's a concrete thing involving maximal chains of posets, where instead of looking at just this homology, you end up looking at a representation in some sense, at least for the examples I'm thinking about. So for example, what's the multiplicity of the trivial representation, and if you look at the partition lattice and the permutation group action. Okay, so how is this related to anything we're talking about, right? So the lift we mentioned earlier is a certain non-commutative generating function for the maximal chains in these rank-restricted posets. And if you're familiar with it, it's a variant of the CD index. So this is where the connection to cross polytopes come from. So you look at the Chebyshev transform we mentioned earlier, so this funny subdivision thing, and you input the ladder poset and you get certain triangulations of these cross polytopes. And as a side note, a funny thing is that historically, if you look at the computation of this generating function, this non-commutative generating function thingy for Boolean posets, you get this descent, skipping double descents, as we see in a lot of gamma positivity examples, Eulerian polynomials, or H vectors of Nestor-Hydra we saw in yesterday's talk by Rick, and those, and also that particular lateral result, if you combine results of Postnikov, Reiner-Williams with older work of Ardila and Reiner-Williams, you also get this same descent statistic interpretation for chowings of certain matroids associated to hyperplane arrangements built out of root systems in a certain way. So it turns out that if you take this generating function and just keep one of the variables and send the other one to 1, we get the Chebyshev polynomials. So that's all I wanted to share today, so thank you.
Thank you. Are there any questions? Okay, then we'll now have a coffee break until